Hello and welcome. I'm Steph Winwood, Head of Corporate and Investor Relations at Blue Glass and the moderator of today's session. On behalf of Blue Glass and Share Cafe, it is my pleasure to welcome you to the third of our expert roundtable sessions, where we continue our deep dive into global trends, opportunities, and challenges in the global semiconductor industry. In today's session, Laser, Modern Warfare's Strategic Weapon, How Light Could Be the Defense Sector's Most Ubiquitous Tool, we are shining a high-power spotlight on the growing role of laser technologies in advanced intelligence and warfighter capabilities within the defense and national security sectors, and the broader impact of defense innovation in transforming our day-to-day lives. Advanced laser technology underpins global defense and security capabilities. The defense sector deploys cutting-edge laser systems in a variety of essential applications, from communications and computing, exploration, ranging, advanced manufacturing, to weapons guidance, directed energy, and countermeasures. Laser technology provides high accuracy, rapid transversal, precision manufacturing, and enhanced intelligence gathering to support both the combat and non-combat needs of the military. These enhanced advantages, combined with rising geopolitical tensions, are driving rapid global demand, with the military laser systems market purportedly worth US $5 billion in 2023 and predicted to reach between $7.5 to $8.7 US billion by just 2028. Joining me today is a panel of highly credentialed laser technology pioneers and defense sector experts from Australia and the US. It is my pleasure to introduce you to Professor John Muth, Distinguished Professor of Electrical and Computer Engineering at North Carolina State University, NCSU, and Director of the Claus Hub for the Microelectronics Commons. Professor Muth has a PhD in condensed matter physics from NCSU. He specializes in optoelectronic properties, materials, and the fabrication of novel photonics devices, making contributions to the advancement of wide bandgap and ultra-wide bandgap materials used in lasers, radio frequency, and power electronics. Professor Muth is a military veteran, having served as a submarine officer on fast attack nuclear submarines earlier in his career, before being called back to active duty in Iraq, where he led a team embedded in the Iraqi Ministry of Interior. Professor Muth has received a variety of academic awards and military medals, including a Bronze Star for meritorious service in Iraq. We are also joined by Chris Donaghy, Chief Financial and Chief Operations Officer at Applied Energetics, a developer of advanced optical technologies and ultra-short pulse laser directed energy solutions. Prior to joining Applied Energetics, Chris held senior roles at defense contractors SAIC and KeyW Corporation, working on national security solutions for the intelligence, cyber, and counterterrorism communities. He was previously the #1 defense analyst and #2 analyst overall for stock selection by Forbes in 2005. Chris also served in the US Navy Reserve, analyzing missile guidance, control systems, and advanced electronics of short-range ballistic missiles. Dr. Jay Daniel is the co-founder and co-CEO of AIM Defense. Jay is a world-leading laser scientist with more than 15 years' experience at the cutting edge of laser technology for defense, industry, academia, and medicine. He has a doctorate from the renowned University of Southampton on 2-micron laser sources and high-power laser design. As co-founder of AIM Defense, Jay has led the development of revolutionary fiber laser designs that reduce size and weight while also making high-power lasers safer. Dr. Patrick Rumaya is a senior optical scientist at Applied Energetics. He has over 14 years' experience in the development of state-of-the-art high-power lasers and optical systems used across manufacturing to science and defense. At Applied Energetics, Patrick leads development programs to leverage technological advancements, including the availability of wavelength flexible GaN lasers. His previous roles include scientist and engineer at Fibertech and Lockheed Martin Space, focusing on fiber lasers and optical systems for advanced sensing missions for maritime, aviation, and space. And we're also joined by someone who may not need much of an introduction to many of you on this call, Jim Hayden, the CEO of Blue Glass. Jim is an expert laser executive with over 3 decades industry experience. He's held senior executive and advisory roles at leading laser companies Kyocera SLD, Enlight, Coherent, and JDS Uniphase. Thank you so much for joining me today, everybody. We will have some time for audience questions for the panel. If you do have a question, please type these into the chat box. So to kick us off with this panel, my first question today is for John, Professor Muth, who brings a unique broad spectrum defence perspective as both the decorated veteran and now in his capacity at NCSU. And as a director of the Claws Hub, one of 8 innovation hubs in the US Department of Defense's Microelectronics Commons. Technology and digitalization means that today's battlefield, compared to just a decade ago, is unrecognizable. Strategic dominance now relies on smart, fast, portable, and highly configurable defense platforms and capabilities versus old-fashioned might. John, can you give us a high-level overview of the application of lasers in the defense industry and what role laser technology has played in this evolution?
Sure. Let me preface by saying that these are my personal opinions and they're not representing the U.S. government or the CLAWS program or microelectronics comments. The defense sector is a essential pioneer for many technologies. Many of these are dual-use technologies. If we look at the history of lasers and the investments that have been made in the laser programs, it dates all the way back to the initial inventions with investments by the U.S. Navy. If you take a look at the broader spectrum of investments with the CHIPS Act, with Microelectronics Commons, with ARPA-E and DARPA, you can see that lasers and associated technologies are a common theme over, say, the last 30 years in terms of being able to advance technology and to be able to maintain a technological edge. What I think we're seeing today is a kind of phase transition in warfare. We have a much wider variety of different types of conflict, ranging from very low intensity to potentially very high intensity, peer-to-peer, near-peer adversary type things. If we take a look at the requirements for operating in a multi-domain environment, air, space, land, undersea, it's a much more complicated situation and covers a wider range of activities than what we would have seen in the past. And so that means that we need to be more flexible, more adaptable, work with our allies, be able to cooperatively advance technologies to maintain our freedom and democracy. So if we take a look at the wide range of applications of lasers, we tend to think of lasers as death rays that are going to knock things out of the sky. But really, it's much more broad than that. It ranges from very high bandwidth communications. It ranges to being able to range and target and being able to see the battlefield in new ways. It's the ability to use these types of tools for secure communications, understanding the environment that you're in, and just to make things work that the warfighter can use on his person or in his system that he's fighting from. So if you start to break it down, we've seen increases in the frequency of the way we can transmit information with lasers, both through free space, through fiber, or through chip-to-chip for applications like AI that are another big thrust. We've seen tremendous innovations in the ability to have laser beams go through the atmosphere to be able to image and see targets. We've have tremendous advancements in the power of lasers and in the type of lasers and being able to put that light where we want it in a controlled manner. So if you take all that together, if you look at the emerging threats, whether it's very fast, small moving boats, or whether it's drones, or it's other types of applications, you see that laser and laser technologies are impacting everything from communications to the targeting to potentially knocking down your adversary.
Yeah, thank you so much. It is really quite remarkable how much innovation has gone on in this space and how versatile laser technology is, not just in defense, but in dual use applications as well. My next question is for Chris. We've talked about how laser technology is transforming the defense capabilities. Why is laser technology such a strategic frontrunner?
Yeah, so it really comes down to the economics of the engagement or the cost per shot. So what does that mean? Well, let's say you have a high volume threat, such as a swarm of drones. Right now, you don't coming at you. Right now, you don't have a whole lot of attractive options to counter that swarm, and we're trying lots of different technologies. We're trying jammers. We're trying cyber applications. There are drones that shoot nets. There are drones that crash into other drones. But ultimately, it might be your most effective solution is a $100,000 Stinger missile. And if you are going to be firing $100,000 Stinger missiles at a swarm of commercially derived drones that may have cost $1,000 a piece, it's almost guaranteed that you're going to run out of bullets before they do. So lasers change those economics. And even though the laser itself is a fairly expensive piece of hardware, the cost of each bullet that is associated with that system is very, very small. However, I would caveat that a little bit because we've been talking about the advantages of lasers being deployed onto the battlefield since the thing was invented in the 1960s. They've always been the next big thing. You know, lasers are going to be the next big thing in 5 years and 10 years. And we've been saying that for decades. And yet we still don't see them widely deployed anywhere on the battlefield. So in my opinion, for lasers to become widely deployed on the battlefield, I believe you need to see the convergence of three things. First of all, you have to have a threat type that is uniquely suited to being countered by the effects that a laser can produce. Second, you obviously also have to have the lasers that can deliver those effects. And again, that's never really been the problem. The third and missing leg to the stool is you have to be able to deliver those effects in a size, weight, and power footprint that allows you to put those lasers anywhere you want to. If you were to see the size of, Lockheed Martin's 300 kilowatt laser, it's mind-boggling how big this thing is. And you can see, and the cost is even more mind-boggling. And so the combination of both the size and the cost, you're just not going to be able to put those things anywhere you want. So until you start to see systems emerge that have a size, weight, and power footprint that makes sense, and you can deploy those systems onto on virtually any platform you want, whether it's one of the side-by-side Polaris razors that the special military forces use or naval ships, you're not going to see widespread deployment of lasers.
Yeah, it's very critical, that size, weight, and power swap, as it's referred to in the defense for our investor audience. And it is really interesting to see those novel technologies that will help enable the downscaling of those laser systems. And we have a few people on this panel who will be able to talk to that today. So we're very lucky. Can you tell us a little bit about how Applied Energetics is working in this and how your advanced laser systems and target markets are reducing the swap in the industry?
Yeah, so Applied Energetics is focused on a specific kind of laser called an ultra short pulse laser. And the damage mechanism of an ultra short pulse laser is different from the continuous wave lasers that most people think about when they hear the word laser used, especially used on a battlefield. And I don't want to get too deep into the math here, but if you compare the peak power, so let's take a 10-watt continuous wave laser and compare that to a 10-watt ultra short pulse laser. So a 10-watt continuous wave laser, it's useful for laser engraving. It's not something that you're going to find anywhere on the battlefield. It's not a very useful device because the peak power of a 10-watt continuous wave laser is 10 watts. In ultra short pulse land, it's a totally different story. A 10-watt laser in ultra short pulse characteristics will produce a peak power of 2 billion watts. And again, I won't get into the mechanisms of that. It kind of hurts your brain. I'll let you do a one-on-one tutoring session with Pat Ramaya if you want. He can explain to you how those numbers get derived. So 2 billion watts though for the same average power. So it has a different kind of kill effect. And the application that we're going after initially is counter ISR or counter sensor. And specifically what we're doing is we're targeting the electro-optic sensors or the cameras on unmanned systems, whether it's an aerial drone or a ground drone, and we're targeting those cameras at tactically relevant ranges. So it's not something where the thing has to be 5 feet in front of you. We're doing this at a range that the military would find useful. So the long and short of this is we're able to destroy the cameras of incoming small drones at a sufficiently long range, and we can defeat those cameras in less than a second. So if you have a swarm coming at you and you're at a tactically relevant range, and we're doing a sub-second kill of the camera, we are significantly degrading the capabilities of those drones as they get as they try to cause their effect. And we're doing this now, most importantly, going back to the 3 legs of the stool that I described earlier, we're doing this in a size, weight, and power that is 2 orders of magnitude smaller than the traditional high-energy laser systems that are being used for a similar application. Think something that's roughly the 8 inches by 8 inches by 14 inches, but it consumes about the same amount of electrical power as your garage door opener. So we're able to do this in a very effective footprint, and it's really that 3rd leg of the stool that is the secret sauce of what we're trying to do.
That is absolutely amazing, absolutely amazing, and I cannot believe that you take a 10-watt and ultra short pulse, turn that into an output equivalent of 1 billion. That is amazing. My next question is for Patrick. You're an expert in directed energy and tracking technologies. Can you explain what a directed energy weapon is and the systems that sit under that umbrella? Is this technology currently used in modern warfare, or is it still in development?
Sure. So broadly speaking, directed energy is any kind of electromagnetic source that is intended to create an effect at range. This, broadly speaking, can include the canonical example of very high power CW lasers like the Lockheed systems. It can be high power microwaves, which are occasionally pursued. At one point, they were pursued as a deterrent for large groups of people that fell off the wayside and was never deployed. It can also be used as swarm destruction, sensor destruction. Rigorously, you would include power beaming as well under this umbrella, which is not given as much attention as directed energy weapons. It's not a weapon so much. And rigorously, you would not include sensors, some kind of LiDAR solution. But because practically they use very similar technologies and the same people are making them, practically they are often under the same umbrella, even if it's LiDAR, something that's not intended to affect the target. And then there's also more difficult, complex solutions, such as laser-guided electrical discharge, where you use a laser to produce a plasma in the air and actually impart basically an electric shock through that plasma channel. And right now they're on the cusp of deployment effectively. You have systems are mostly in the testing phase, and then there are a few actively deployed in at least the U.S. military. I have no idea about the Australian military.
That's great. Thank you. A key advantage of these high power and directed energy industrial lasers is that they have an infinite magazine, so where they can keep firing as long as they have electrical power. However, laser weapons need to operate with rapid effectiveness across long ranges, which is what Chris was talking about previously, and in contested environments. How are you innovating to overcome these technologies hurdles?
Sure. So the first obstacle is relatively simple. The first obstacle is just called the diffraction limit. Effectively, if you want to make a small spot very far away, you have to have a large aperture to start. So if you're trying to, which is why you'll see, for example, imaging telescopes for large observatories might be very, very large. It leads all into the diffraction limit. There are clever solutions to defeat that in the nonlinear regime, and ultra short pulse lasers can do that in certain cases. But in general, even for the CW lasers, a reasonable aperture is sufficient for tactically relevant ranges. The more difficult obstacle is turbulence, which is just in the air, small variations in atmospheric pressure, which lead to small variations in refractive index, which end up breaking up your beam, making it very difficult to maintain a small spot at great distance. And what it ends up doing is make your beam effectively larger where you're hitting, and so your intensity is lower. And if you have a intensity dependent effect, which almost all directed energy solutions are, that'll eat your lunch. Our critical innovation is first just requiring less average power, so we can have if we are 10 times, if we have say 10 times the diffraction limit requirement for power in our system, that's still an achievable system versus if you have something like a Lockheed Martin system. If you said you have to have 10 times the required system, suddenly you have a miracle laser that's 50 years out, because they are already on the limit of what is practically achievable for a large CW system. The other things that we do, we have a lot of wavelength agility and pulse shape agility, because we can control the pulse format, including having a burst of pulses and having pulses of different durations, as well as having different colors. We can optimize for the effect on target. Beyond that, we are also looking into clever solutions to defeat turbulence, basically, in a more elegant solution than is currently employed. There are solutions not solutions, but mitigating solutions to turbulence, including beacon illumination and adaptive optics, which are used to measure the wavefront error created by turbulence and then correct it back at the source. And those are great, albeit generally fairly expensive systems. We're looking at more elegant solutions that all lead into our multifunction aperture, where we can track wavefront correct and damage using one aperture.
Yeah, that really speaks to the opportunities and also the options to innovate to overcome these hurdles. My next question is for Jay. AIM Defence is a brilliant example of world-leading innovation developed here in Australia being deployed in the global defence market. Can you tell us about how your high-powered directed energy systems and how you're commercialising Australian innovation into global defence markets?
Yeah, thanks, Steph. So AIM's built around the proposition of how do we protect 5 people in a vehicle against modern threats. So Chris kind of talked about this value proposition really well. The reason directed energy is becoming so important at the moment is we have an asymmetric threat in weaponized drones. So we're seeing this in the invasion of Ukraine. We see it globally. Essentially, it's a threat type that defense isn't used to. So typically, defense threats are developed by peer adversaries. Technology moves on the 3 to 5 to 10-year scale, and that cat and mouse game of measure and countermeasure happens at a managed pace. With weaponized drones, the main challenge there is we're seeing major companies spend billions of dollars a year and making these systems amazingly well. So what we're trying to do at AIM is essentially counter these very well-funded, very low-cost COTS drones. So the way we do that is we throw out the book, essentially. So typical directed energy programs have said, how much power can we use? What effect can we have and at what range? So, for example, counter-ICBM, counter-missile, CRAM. We're thinking the same way as I'd say applied energetics is, in let's manage the problem, let's bring that in and say, okay, well, we want to protect 5 people within a kilometer range. And when you start to look at that as your design space, you get a lot of benefits. So one of the major benefits there is our system is about an order of magnitude cheaper than everyone else. So we've done that by saying we don't need to be at 10 kilometers. We don't need to worry about that super turbulence. We just need to protect the vehicles at the 1 kilometer range. We've also rolled in some other usability things, like we're really heavily focusing on eye safety and usability. Part of that is novel wavelengths. So as you mentioned, my background is in enhanced eye safety 2-micron lasers, but also in deployability. So there's no point in having an amazing directed energy system that's the size of a shipping container that you can only deploy once. It really needs to be a strategic asset or a tactical asset rather than a strategic asset. So we're starting to use the terminology tactical directed energy. And what we mean by that is directed energy that you will deploy on a day-by-day basis where the battlefield most needs it. And so our current version of our system, Fractal 1, we're calling that boot portable. So 2 people can carry that outside of a car, stick it on a battlefield. And ideally, you don't actually want to be near your directed energy system because that's a high value target in an asymmetric battlefield. So you leave it there, you walk away. It provides a barrier and a shield to that area. So essentially, that's the kind of value proposition of AIM. And what we're finding is most NATO allies, most middle powers really resonate with that. They can't afford the $20 to $100 million directed energy systems that the superpowers are putting money into. And so we're really finding this, one, it allows customer to understand directed energy in a much better way, but two, it actually solves a real threat that they're seeing in the battlefield right now.
Yeah, that's really amazing. And that asymmetric threat type with new technologies such as AI and quantum is only going to increase. So the approach to innovation is also going to have to continue to keep up as the defense battlefield evolves. My next question is, part of how you're bringing this boot portable and tactile directed energy is that you're using, you combine sophisticated AI and high-powered directed energy lasers in, that game-changing portability. What next for AIM?
Yeah, good question. So as you said, we combine AI as well as a number of other algorithms to really precisely track. So whereas a typical directed energy system would go for a center of mass, hit the middle of the drone, we actually hit individual parts of the drone. We look at a vulnerability map of the target and say, where is the most useful part to hit within the current time? And what that's led us to is reduce the required laser power by about an order of magnitude. So rather than needing these 30 kilowatt lasers, maybe we can get away with much lower power. On the laser side, what that means is typically, I would say in this room, people would probably have a really good idea. Laser cost roughly scales as laser power. So if you need 10 kilowatts, that's a $10 million system. If you can get that down, it's going to be much cheaper. So what we're doing is we're using directed energy and defense as our first market. Defense is an interesting customer where they have unique problems. Often in the world, they may be the only person with that problem. And they understand that, and they're willing to spend a significant amount of money for the infrastructure and setup costs to solve those problems. But ultimately, defense is a tricky customer at which you're dealing with government-type timescales. And so we move on into more interesting industries. For us, that's industrial manufacturing and processing. So once we get past that first step of building up our manufacturing capability, our next step is moving into the more traditional markets and essentially using that combination of lasers and AI to disrupt those markets as well.
Yeah, defense innovation really plays such a critical role in those dual use and traditional civilian markets as well. That's really important point. Jim, we've talked about the applications of lasers in defense in general. Can you provide an overview of what role visible lasers and blue glass will play in defense applications?
Yes, thanks, Steph. I have to fight the urge to not answer by saying what they said because I really like all of their answers. So I'll try to add a little different color to it. So visible lasers, basically they'll share the field with IR and UV lasers, the non-visible lasers. But what visible laser and blue glass technology, they'll be used in, or they have potential to revolutionize many aspects of national security applications. And they run the gamut from weapon systems, drones and autonomous vehicles, war fighter outfitting, like John had mentioned, and then into the intelligence and security measures. In weapon systems, for instance, visible lasers can be used in target designation, range finding, aiming in various weapon systems, and they also in those applications they enhance sort of the accuracy and precision. Are you getting it like tightly together and where you want it? And so those types of things are where they come into the weapons areas. And then drones and autonomous vehicles, we've heard a bunch of the different things that it could do, but visible lasers can aid in navigation, obstacle detection, the communication between the drones and ground stations. It could be very secure and very efficient with visible lasers. Also, they're relatively inexpensive. When you hear some of the economics, countermeasures to disable incoming autonomous vehicle cameras and so forth. again, at the warfighter outfitting level, laser sights, illuminators, rangefinders, they all improve situational awareness for our soldiers. And then in the intelligence community, the secure communications and so forth, quantum computing, quantum sensing, artificial intelligence for modeling and simulation, cryptography, where you create these keys that are nearly impossible to decipher. So they're great in both defensive and counter-offensive communication systems. So in summary, I think we could come back and say what they said, but I would like to say a little more detail. Visible lasers and blue glass technology contribute to these critical defense capabilities, spanning from precision targeting, advanced photonic systems, such as navigation, designation, detection, quantum computing, and in quantum computing, and which drives artificial intelligence and empowers our defense by fortifying communication, optimizing the operations through modeling. When you're putting logistics together and you've got these complex artificial intelligence programs, it can help you figure out different situations, run scenarios, and you do it much faster than conventional computing. It helps with situational awareness, and also advancing other technologies. And these technologies that we are addressing, they're dual use. So these can be used both in commercial and national security markets, and they foster the next level of innovation as well in those in both areas. So it's pretty exciting for us.
I imagine that securing your covert communications so that you can maintain that strategic environment while also, really understanding your battlefield has got to be critical to maintaining survivability and lethality in the digital war space that we're in now. My next question is for you, John. The defense sector is an essential pioneer, not just of strategic capabilities, but also commercial energy, space, aviation, and health technologies. In the US, this is supported by robust policy and investment by key programs such as CHIPS, Science Act, Microelectronics Commons, DARPA, ARPA-E, and others. Can you tell us about the US interest in reshoring strategic capabilities and manufacturing?
So, again, this is kind of taking a little bit of a historical perspective. If we look back at how technologies have been invented, the U.S. has had a history of leading different innovations, being able to put them into different systems, both for defense uses and for commercial uses. And we drifted away from that in terms of offshoring, largely for consumer type applications. But as those consumer applications went offshore, then some of the underlying technical capacity that we had to do other types of manufacturing moved offshore. And so, we now have a situation where there's a much broader recognition of the worldwide competitiveness, the landscape, how do nations compete economically, and how do they protect themselves from a national security perspective. And what we've kind of discovered is that for the well-being of our citizens, we need to have good jobs. We need to have the know-how to be able to make stuff, and that's a critical component. And then for that tying into both the national security and for economic competitiveness, we need to understand what the supply chain looks like. And so when we take these things into a consideration, it becomes a important consideration when we find chips that have been compromised in, say, communication systems, or when we find that we have to purchase something where we would really like to keep the intellectual property to ourselves. We see that proliferation of technologies level the playing field where maybe we would like to maintain a certain advantage. And so this is where I think you take these as in aggregate, you see that it becomes a comprehensive strategy for the United States to want to bring certain types of manufacturing in particular back to the U.S. Again, not just for to achieve a specific tactical or technical goal, but for the well-being of the citizens and being able to protect them both economically and from national security perspective.
Yeah, that's great. So this leading defense policy and investment has really far-reaching strategic and economic benefits for the US. Given the obvious benefits of investing in sovereign manufacturing and reshoring supply chain and capabilities, what can Australian policymakers learn from the US and European programs to bring academia, government, and industry together?
Yeah, that's something I think is extremely important. And I think that you can see that there's a diversity of approaches. If you take a look at the European approach, it's a little bit different than the US approach. If you take a look at, say, things like the Fraunhofer Institutes, you may have more of a idea of being more tightly connected to a manufacturing and next generation manufacturing. If you take a look at institutions like IMEC or other things, you'll see a lot of large investment by industry into specific areas in kind of a coordinated manner. If you take a look at how the U.S. Has been doing things with manufacturing institutes, where they selected targeted areas that were important and assembling kind of teams of academics, industry, and government together, those typically tend to be smaller, and they tend to want to also leverage cost sharing and industry involvement. But a lot of it's also about communication. How do you bring the academics, government, and industry together and then have them communicate? So at NC State with Power America, we now have a consortium of about 80 companies that regularly communicate about power electronics. That's an example of where there was a certain amount of funding that brought things together, made technological advancements, and then there's still communication. So I'd say in addition to kind of a diversity of approaches, because each type of technology is a little different, you also want to have a longevity to your approach, that a small investment for a short period of time isn't necessarily going to cut it. If you take a look at the investments of a variety of countries around the world, sometimes if you have a nation state that's willing to put a lot of money into one particular area, that can be a competitive advantage for that country in that technology. And so when you look at how Australia or the US or Europe can work together, I think that you have to be selective in the technologies you want to invest in. You have to choose time periods over which that you can have sustained investment. And I think that you also have to have a diversity of approaches and tailor it to the particular industry that you're looking to bolster.
Yeah, that's really key. Australia is, due to our scale, going to have to pick some technology winners such as quantum, photonics, and laser, hopefully. So that's really, really interesting. Jay, I'd love to get your views on navigating the Australian defence ecosystem. It's often said that it's easier to get Australian developed technology accepted into US defence supply chains than into Australian defence supply. What can the sector do to ensure that Australian defence is better leveraging innovation developed here in this country and our manufacturing capabilities?
Yeah, thank you for the question. I would echo what John said and what you said, actually. Let's pick winners. Within defence in Australia, we need to pick focused areas. Photonics, Blue Glass, AIM, there are a number of companies that do that really well. And figuring out how we foster those and realize it's a long tail to get to where we need to be is probably how we'd move that forward. Our journey has been very closely aligned with defence. So from day one, we've worked with Air Force and Army. So Air Force sponsored our first indoor test range. Army provides amazing input on tactical strategy as well as form factor. So my advice for Australian companies would be find customers that really have a problem and make them work with you as much as possible. And for us, what that looks like is we've had 4 years of continuous contract development with Air Force, Army, and Defence Science Technology. Actually, our latest one, proudly, is a joint project where both Army and Air Force paid money, and anyone that's worked with Defence understands how hard it is to get Air Force and Army to put money in at the same time. And that gives you an idea of the breadth that photonics can offer to Defence. Figuring out how we do that in Australia is a challenge, but we're getting there. Programs like ASCA, so ASCA has above $1 billion of money under management with a strategic goal to create capability in Australia. Fostering those programs, make sure that they're not year-by-year decisions, they're long-tail decisions to say, we're going to invest in a capability and we're going to expect returns in 2 to 5 years, not 1 year. I'd say they're probably the first steps.
That is really, it's super interesting. It's really encouraging, though, hearing how collaborating with Defence has been so successful for AIM. So that's a really great case study. And yeah, it's really exciting to see that breadth of what photonics can offer Defence. My next question is for Chris, and coming back to the opportunities. Are you able to give us an idea of the size of the market for laser systems in Defence and the national security sectors? And do these technologies have commercial applicability as well?
Yeah, so you mentioned a few numbers earlier to kick the meeting off, and it's no surprise there's plenty of market research organizations out there that will gladly sell you a report for $4,000 or $5,000 to tell you how big they think the market's going to be. But if you look at counter drone, for example, today it's just under a couple of $1 billion, but is expected to grow to about $7 billion by 2030. It's about a 20% growth rate. Similar type of growth rate for the directed energy market, another 20% or so, supposedly growing to $18 billion by 2028. Again, particularly this latter market, I just want to reemphasize that it's going to take additional capability development that focuses on how do you deploy this more broadly in order to see that kind of market growth. You're not going to see $18 billion of systems that cost $300 million a piece in 3 shipping containers that are sitting ducks in a deployed situation. You're not going to see many of those show up. It's really going to take different approaches like what we're doing with ultra short pulse lasers and what Jay is doing at AIM Defense. I think that these 2 approaches, the 2 you've heard today, stand a much better chance at creating the inflection point of the adoption of these technologies than it is the traditional approaches, because the traditional approaches, they've been doing it for 60 years, and you still don't see them. So it takes a different way of thinking, and with that different way of thinking, now combined with this unique threat environment, that's what's going to see or cause the growth in the market. We do have commercial market opportunities as well. Ultra short pulse lasers, the capabilities we're developing will have applications in the biomedical imaging market, for example. Also, we believe there's an advanced manufacturing application as well. We're likely going to stay pretty focused on the national security market for the time being, but we do see commercial market opportunities as an attractive market to be in someday as well.
Thank you. Yeah, that's really interesting. Jim, I wanted to understand what role quantum technologies will play in next generation defense and dual use applications.
So the quantum applications is the question, correct? So there's, I guess it's important to understand, maybe 3 main areas of quantum computing, quantum sensing, quantum communications. I think we've discussed these throughout this, but these areas are vital because they form the basis for things like quantum cryptography and secure communication, cyber security and offensive capabilities, and so forth, simulations, sensor technology, machine learning, materials technology, and so forth. Some of the specifics, if you look at quantum cryptography, they have something called quantum key distribution, or QKD. These quantum computers can generate these unbreakable encrypted codes And these keys are used, they're based on the principles of quantum mechanics, and they're basically immune to the classical attacks, from standard computers and so forth. This ensures secure communication channels for military operations. Quantum resistant cryptography is basically these computers that threaten classical computers or so forth, or if you're being threatened by other quantum computers, you have to develop quantum resistant cryptography methods that are very crucial, because we're not the only ones out there doing quantum computing. So it has to work both ways. You have to be able to protect against other quantum attacks as well. And so the cybersecurity and offensive capabilities, when you're breaking classical encryption, quantum computers can crack these codes much more easily. And so they're exponentially faster. So the nations with quantum computing capabilities are really going to gain the edge. And so with quantum attacks, these algorithms that can break them allows others to get into our communications, and having these countermeasures, basically makes us much more secure. And then as far as simulation and optimization, when you're doing these sort of modeling programs for missions, planning, logistics, quantum computers excel at solving these really complex problems. How do you have all of these different technologies, or maybe even these different nations coming together, so they could basically optimize troop deployment, supply routes, resource allocation, and so forth. And then you gotta count for Mother Nature, right? So how do you model what's going on in the climate? You have to be able to look at the simulations to enable accurate climate predictions, and also have to understand what's going to be happening in the terrain, and different threat assessments when you're going into places that maybe you haven't been before. And then we come to sensor technology and target recognitions. So quantum sensors, they exploit quantum properties to detect subtle changes in physical environments, like gravity, magnetic fields, and so forth. And so they can enhance surveillance, early warning systems, and provide threat detection that we didn't have the capabilities before these technologies. They're really interesting. These sensors are so sensitive that they could detect the pulses from your nerves, and so they could be used for remote controlling things like prosthetics or autonomous vehicles. So those are really some really interesting technologies, I think, that are being advanced by this quantum technology.
It is really quite mind-blowing how quantum technologies are going to change the game. So that's really interesting. Thanks, Jim. We're getting some questions from the audience, and the first one that I actually want to put to John is there's lots of questions around the how the US can collaborate with its allies, how these programs are working, and how AUKUS countries like Australia and the UK can participate in these sorts of programs. So my question for you is, to ensure that the US and its allies do have access to state-of-the-art security technologies, including a lot of the laser areas discussed today, how critical is research and development collaboration, and how can we best ensure leading edge technology is developed with strategic allies?
Yeah, I think that's a very interesting question, and I think that part of it is that science is a community-driven enterprise, and at the basic research type level, you can have more freedom of communication, dialogue. You can talk about things in a pre-competitive space, and by pursuing that type of dialogue in critical technology areas, it leads naturally to more collaboration at higher technology readiness levels. And for example, it can provide introductions to being able to work with people at national labs, or to be able to work with as was mentioned earlier, the Army or the Air Force on a technological problem that's of interest. So the Defense Department, Department of Energy, National Science Foundation, all of these agencies encourage some type of communication and dialogue at the basic research level for technology areas, especially in photonics and other interesting areas.
I love that. I love that science is a community-driven process, and that it takes that strategic collaboration, but also communication to take game-changing innovation to real-life applications. To turn ideas into applications. Do we have any more questions coming through?
Yeah.
Okay. So getting some more questions around the directed energy. So I'll put this to Patrick. Why is it only recently that direct energy weapons are being considered alternatives to traditional munitions?
Sure. That's actually a really good question. So there's obviously the lag between a technology readiness and then a deployment, and that's going to be the bulk of the problem. But fundamentally, the factor that has advanced to the point where this becomes practically usable is high-power diodes. Realistically, the fundamental enabling technology for all, I say not all, but the gross majority of directed energy weapons is high-power diode lasers, usually 790, call it from 790 to 1 micron. And those things support high power fiber lasers, which are suddenly compact and robust enough to deploy. And whereas high power lasers, extremely high power lasers, have existed for longer than that, they are, when you take into account the deployment lag, which is huge, right? Take into account deployment lag, just now getting to the point where they are powerful enough to do something when combined into a directed energy system. So practically, and then also right now, we have threats that need it dramatically. That the suddenly new threat of a drone creates a sudden uptick, but it had been intended for use against missiles, small boats, and whatever for a very long time, and still defeating all of the small problems, defeating turbulence, and having enough power to make the impact. It's just has taken this long in linear development. That's why we're trying to go a different route with a solution that has the same level of robustness. We are also using, for the most part, fiber lasers or something very robust and compact. But it's a different solution that should not have to be combined into a massive shipping container to be usable.
Historically, lasers have been about shooting down Russian ICBMs. If you go back to the early days, the 80s, part of the Star Wars initiative was putting lasers in space and things like that to shoot down Russian ICBMs. We invested billions of dollars into a 747 that had a massive chemical laser, where they were going to deploy a massive chemical laser inside it to shoot down Russian ICBMs. The threat has evolved, as Patrick said. The number of threats that are vulnerable to high energy lasers and ultra short pulse lasers is proliferating like crazy right now. And we can't keep up. We can't keep up with the traditional approaches to how we're countering those things. The types of weapons that we're using to counter the Houthi drones in the Red Sea, we're going to run out of bullets. And that's why you see organizations like the Navy clamoring for high energy lasers now. They know that they only have so many SM-3s and smaller missiles to fire against those types of threats, and we'll run out. We will run out of bullets.
I think that is just the perfect perfect place to leave it, because it's such a compelling opportunity that you've outlined there. To wrap it up, I'd like to get some final thoughts from the panel on the emerging opportunities to support what Chris and Patrick have just said. Jay, where do you see the opportunities for laser technology and defence energy and national security? And does Australia need more sovereign manufacturing capability of these technologies onshore?
Thank you. I think I'd echo pretty much what Jim said. Everything this panel has said, I agree with. We're singing from the same playbook here. We are at the beginning of that hockey puck curve for directed energy within defence. Defence has traditionally operated and adopted new technology very quickly. This is a new type of force, so it's very interesting for defense and it's able to counter a very growing threat. And so we are at the start. And so I would expect for us, the majority of the next few years will be absorbed by figuring out how we deploy our system, develop operational tactics, usability, that kind of thing for the system. Longer term, the same reason directed energy is interesting for defense, so is photonics. As Jim said, communications, counter communications, there's that cat and mouse game where photonics essentially opens up the space on both fronts. So for us, we think we'll be busy in that space for the next few years. Beyond that, should we develop it in Australia? I mean, the answer is yes. As a sovereign country, we need an assured supply. So from that standpoint, from a direct defense position, we have to be able to manufacture our own things for a critical need. But also there's a benefit there. Australia has typically punched well above its weight when it comes to innovation. You can see that with Blue Glass and the amount of power that they're getting out of, or you guys are getting out of individual diodes. Very rapidly, you will dominate that market. We see the same thing with directed energy within the area that we're focusing on. It's that playoff between we don't want to boil the ocean, but there are areas that we can excel at and we can develop. One, that's great for Australia, but also it becomes a trading chip for the rest of the world. So if the rest of the world wants access to our technology, there's deals to be made there. We see it as a very, very exciting future for directed energy and photonics in Australia, and we're pretty excited to see where that goes.
Yeah, we couldn't agree with you more. And we want to see, more companies like Blue Glass and AIM having that real ambitious technology roadmap that we're developing here on shore. That's really, really exciting. Patrick, just wanted to get some thoughts from you quickly because we're running out of time. But what are some of the biggest breakthroughs in laser technologies that you've seen in the industry? And how does collaborating with companies like Blue Glass help you integrate, very disparate novel technologies into next-gen solutions?
Sure. So like I said, the enabling technology for defense-related lasers, broadly speaking, as they are today, is the diode technology that allows for these lasers to be compact enough and high enough power in a diffraction-limited modality to be usable. And though there are several applications that we're already working with Blue Glass to develop in the sensing regime, what I need to express here is that having access to an entirely new regime of flexible pump diodes opens up an entirely new era of effectively photonic discovery. You have the same way 1 micron, 1.5 micron, and 2 micron fiber lasers develops, call it since 1995, after those diodes were developed into a quality product. We're going to see an entirely new branch of lasers. There's applications for direct diode that I'm sure Jim has hammered a million times into everybody's head, and he knows them better than I will ever. But as far as using them as pumps, the sky is the limit is effectively the case. Just for off the top of my head, if people have already shown at low power mode locked fiber lasers in the visible regime, and that is exactly what you need for subsurface naval LiDAR. And it's something that, with access to a quality diode product, becomes a robust, compact solution, a tenth the size and a tenth the price of what would otherwise be available.
Yeah, I love that. A new era of photonic discovery. That's great. Pretty exciting. Jim, we're still getting some questions around, how do we take these really exciting defense applications, and in particular for visible lasers, how do we take them into civilian applications? And I think, you've touched on this with the quantum computing and quantum sensing applications. And I think summing that up for the audience would be really helpful.
Right. So I think the dual use nature of this comes into light if we listen to what each of my colleagues have said here today. They talked about, the 10-watt laser that can be used in a just a marking application, right? Or, processing PC boards, which go into everything. You could take that laser, put it in blue color, and do something that would take IR light, 3 to 10 times that amount of power, and you could do it with a third of the, basically a third or of the power, a third of the time, and you could do multiple applications because the visible light is absorbed so much better in different kinds of materials, where they, in the past or even most of the present, they'll do those processes with 3 different IR lasers. So it's much more expensive. And you can take that same 10-watt laser and put it into a pump and then get billions of peak powers out of it. And so it can be used in the dual use nature. So things in the quantum computing areas, like you mentioned, to just do processing of information much more quickly, that's going to help the entire industry that is being driven by communication or information, the information age, right? So if you can compute more quickly, it's going to help people in both commercial and defense applications. Also, when you're looking at things like sensing, magnetic sensing that could be used for prosthetics, that could help people enhance lives that can't use their limbs. And it could also be used for autonomous control of vehicles. Then you have things that are coming with the automated navigation and so forth, all these drones and so forth. So you could use that in commercial and in military. So you could see how what we are doing and what our colleagues are doing has multiple applications in space, underwater applications, in manufacturing technology, and in just keeping our countries secure.
Yeah, that's critical. John, what do you think? You've seen a lot of innovation in your career, and you've seen a lot of change and a rapid increase in the rate of change. Where do you think the next big catalyst and opportunity is?
Oh, I think people always say that the future of lasers is very bright. And I think that's very, very true. The dual use applications, I think, are also a critical part, because when you look at the defense applications, they need to be sustained by often a commercial technology base. And I think that going from gas lasers to chemical lasers now to diode lasers, you have this stupendous opportunity. And the use of, if you think of it in terms of energy conversion, if you are driving a ship along and you have all that energy that you're putting into moving the ship, if instead you take that energy and you turn it into electricity, and then you turn that into a directed energy from a laser, you have a tremendous advantage. And like was mentioned by Chris earlier, you don't have that ammunition reloading type aspect. But lasers are all over the place, and I think it's a great technology and very exciting for Australia and Blue Glass and everybody here on the panel.
It has been such a fantastic panel. We've had some really interesting questions come through. I definitely think there's a lot of interest in this space, so I think we may have to do a follow-up panel on lasers again in the future, because I really appreciate your time. It has been a fantastic discussion. So there are some questions that we weren't able to get to today, because we did have quite a few come through. So we will be sending some emails out to people to help them if they have follow-up questions. We are also looking forward to bringing you our next expert roundtable, which is on highlighting the future of quantum intelligence and Australia's role in the quantum revolution. I want to say thank you so much to the team at Blue Glass who've helped put this on, but also Share Cafe for bringing this event series together. Our expert panel, what a fantastic discussion. It was really brilliant. Really appreciate you lending your expertise for us today. And most especially, thank you to our amazing audience. Thanks for joining us as we talk some pretty cool laser technology and future applications. It's a really exciting and game-changing space. We look forward to seeing you again next time. Thank you.
Thank you, Steph.
Thank you.
Bye, everybody.